Hello viewers, we will discuss the solution of Volter integral equation of second kind by the method of successive substitution. For the solution of Volter integral equation of second kind, we consider a Volter integral equation of second kind as phi of x equal to f of x plus lambda a to x kernel x comma xi phi of xi dxi, which is the integral equation because phi of x is unknown and which is presented in under the integral sign. Here kernel k of x comma xi not equal to 0, then it is integral equation, otherwise it is not integral equation. So not equal to 0, and it is real must be and continuous in the rectangle domain. That means xi and there is x and there is a rectangle in here. Suppose a to b and a to b, there is a rectangle. So kernel x comma xi is continuous and real in the rectangle, and f of x is real and continuous must be in the interval a to b. That means we rewrite the interval as like as a less than equal xi less than equal b and a less than equal x and less than equal b. It makes a rectangle, such types of rectangle, and f of x must be continuous and real in this interval, and kernel must be continuous and real in the rectangle. So now we use a substituting rule for solve the given Volter integral equation of second kind. Lambda must be a constant in here. For substituting, we use phi of xi. When we write phi of xi, then wall x is replaced by xi. So this is lambda and a to xi, but kernel, when x is replaced by xi, then this xi and this xi is mixing. So firstly we have a work. This task is very important where xi is presented in before, then all xi written as a xi1 and x is replaced by xi, then xi and xi1 represent distinguished characters in this equation. So first task xi is replaced by xi1, and the second task x is replaced by xi. So now putting the values of phi of xi in here, then what we get? That means phi of x equal to f of x plus lambda a to x kernel x comma xi, and phi of xi, that means phi of xi, that means f of x, so f of xi plus a to x, but this is xi, kernel x, but this is now xi because xi x is replaced by xi, and this is xi1 and phi of xi 1, and this is xi 1 also, and the integration must be integrating variable, that is xi, and there are a second bracket we use because there are two terms in here, and the plus sign is in here between the two terms. So now phi of x equal to f of x plus a2x, there are a lambda, there are another lambda, and kernel x comma xi f of xi dxi. So the another term, this is the distributive law, lambda square a2x and kernel x comma xi, and there is another integral domain a2 xi kernel xi comma xi1. If we cannot use comma, then it is benefited for seeing this, but this comma written as this form, this is the comma, and phi of xi1 d of xi1 and d xi. So the given Volta integral equation is expand to this by substitution method, and again we substitute phi of xi1. So what's the value of phi xi1? Now since phi of x equal to f of x plus a2x kernel x comma xi phi of xi and d of xi, since we find the values of xi1, so while f of x is sensed and it sends xi1, so kernel x comma xi, this x is replaced by xi1 and phi of xi d of xi, but there are xi and these are xi, the both two xi are mixing, so the calculation convention xi, this is the dummy variable, we replaced by xi 2 and putting the values of phi of xi1. So what situation will be presented in here? So we write what presents in here. Phi of x equal to f of x plus lambda a2x kernel x comma xi phi of xi d of xi plus lambda square a2x kernel x comma xi and a2 xi kernel xi comma xi1, this is comma, and f of xi1 d of xi1 d of xi plus lambda cube a2x kernel x comma xi and a2 xi kernel xi a comma xi1 and a2 xi1 kernel xi 1 comma xi 2 phi of xi 2 d of dxi2 dxi1 and dxi. If we write in general form, then what represents it? For writing in general form, we introduce some general conception. That means when lambda is square, then there are two integral sign, two integrating variable, that's xi and xi1. And when the power of lambda is 3, then the three integral sign and the integrating variable are 3, that xi, xi1 and xi2. So when lambda has a power 4, then there are 4 integral sign and the integrating variable are xi, xi1, xi2, xi3. So now we'll discuss the inner side. That means when lambda is square, then the kernel x comma xi and xi comma xi1. So there is 2, there is 1. And when the lambda has power 3, then kernel x comma xi, x comma xi comma xi1, and then next please see this in kernel xi1 comma xi2. So the last is in first. There is in last and there is in a first. There is in a last and there is in a first ordinates. So x comma xi is an order pair, and the ordinates of and abscissa, ordinates is xi and in abscissa is xi. So ordinate in xi1, the abscissa is xi1 and then xi2, and pi of xi2 in here also. So this is messing with xi2 and xi2. So next we will introduce a general conception of the limit of integral a the lower limit, but xi and xi1 the upper limit. So if we see xi and then xi and xi1, this is xi1. So when this is dxi3, then we can write now the limit of fourth integral a to xi2. So let's go place the general form of this. The general form of this phi of x equal to f of x plus lambda a to x kernel x comma xi phi of f of xi d of xi plus lambda square a to x kernel x comma xi and a to xi kernel xi comma xi1, and there are f of xi1 d of xi1 d of xi, and the general terms, that means we can write the general terms what represent. That means the general term is lambda to the power n and a to x kernel x comma xi and a to what, that is the the integrating variable xi, and so this is the xi in here, the upper limit, that the kernel xi comma xi 1 if, and the third integral a2 xi 1 kernel xi 1 comma xi 2 and a2 xi 2 the kernel xi 2 comma xi 3. Now this is xi 3 and uh, so the last integral, so that means a to xi, since there is a power n, so the xi of n minus 2, this is the integrating upper limit of integration, and there is a kernel of xi n minus 2, and this is xi n minus 1 f of xi n minus 1 d xi n minus 1 d of xi n minus 2, and this is xi 2 xi 1 and xi. Now consider the infinite series phi of x equal to f of x plus lambda a to x kernel x comma xi f of xi d of xi, and the second term of its, that means sorry, third term a to x, there is a lambda square and kernel x comma xi, and the limit a to xi kernel xi comma xi 1 and f of xi 1 d of xi 1 and d of xi. If we write the next terms, that means lambda cube a to x kernel x comma xi and a to xi kernel xi comma xi 1 a to xi 1 kernel xi 1 comma xi 2 and f of xi 2 d of xi 2 d of xi 1 dxi, and like s, and there is s n and s n plus 1 and this, where Sn can be written as, which is already written in the previous slide, but we write in here Sn. What is Sn of x equal to lambda to the power n and a to x kernel x comma xi and a to xi kernel xi comma xi 1 and similarly a to xi n minus 2 kernel xi n minus 2 comma xi n minus 1 and f of xi n minus 1 dxi n minus 1 dxi n minus 2, and this is continuous in xi 1 and xi, the previous is xi 2. If we consider kernel k of x comma xi less than equal p and f of x less than equal q, what represents, that means the wall will be replaced by phi and q. Suppose if this is integrating variable a to x, and there is a function and both are constant, then what represent from here, that means p and q in present is here and upper limit minus lower limit is this form. So if we integrate then another integration sign, so integrate these and this will be written as this form. So now we integrate as this rule when k of x comma xi is replaced by p, that means this is p, this is p, and this is p there, and f is replaced q. So we see that a q is 1, and kernel, that means p is in here n times because the integral sign is n times in numbers. So p is p is n times. So if we write this, then we can write Sn of x less than equal lambda n, and this is qp power n and x minus a power n, and this is n factorial, and this is also less than lambda n and q p to the power a, and if the upper limit is a constant b, then this can be written as this, and this is also greater than this. So if lambda to the power n, that's a constant terms, if and q is the upper value of f of x, and b minus a, b is the upper limit of integral sign and a is the lower limit of integral sign, and n be the constant. So if limiting value n tends to infinite, that is the infinite series, so Sn plus 1 of x equal to 0. So at that position we can say that the given series is converse. If we solve the integral equation by successive substitution, then firstly substitute phi of xi, that means phi of x equal to 1 plus 0 to x xi minus x, and we change the values of xi in terms of x, that means x is replaced by xi. So here 1 plus 0 to xi, and this x is replaced by xi. So the xi is replaced by xi1, otherwise this xi and xi1 mixing in here. So these are all xi1, and we putting the dxi. So only we putting the values of phi xi, that means x is replaced by xi, but when we replaced x by xi, then xi and x are mixing, so xi is replaced by xi1 in before. So continuing these terms, so 1 plus 0 to x xi minus x d of xi plus 0 to x xi minus x, and 0 to xi xi1 minus xi, and we putting the values of phi of xi1. So we get this is 1 plus and integrating limit 0 to xi 1 because phi of xi 1, and we replace the values. X is replaced by xi 1, so xi is replaced by xi2, then phi of xi2 d of xi2, and there is another integrating variable xi1 and xi. If we simulate this 1 plus, if we integrate this, then we get this is xi square by 2 minus x xi, and putting the values 0 to x in here, and then 0 to x xi minus x, and xi1 minus xi, and they are integrating variable d of xi1 d of xi, and using there are two integral, that means 0 to xi. So please write as soon as, and if we simulate these, then we find 1 plus when the values is replaced by 0, that means here xi is replaced by 0, then this is 0, and when we putting the values of x, then now we find x square by 2 and minus x square, so these are the minus x square by 2. So if we rewrite this 1 minus x square by 2, and the third terms and fourth terms, if we simulate this, then we can say that the it is the series of cos x, that means 1 minus x square by factorial 2 plus x to the power 4 by factorial 4 as soon as, and this is cos x. If we simulate the next two terms, then we find this value. So cos x is the solution of the given integral equation, that means the given integral equation is a. So cos x is the solution of the given integral equation. This solution find using the successive substitution method. Thank you very much.